Okay, we're here learning about rotational kinematics graphs. And to kind of help with that, I brought up this silly kind of map that takes all of our kind of vectors that we learned last semester and puts them on a map, and we call it Vectoria. So for a position versus time graph, we call that Positionville. And for a velocity time graph, it's Velocity. And for acceleration, we have Acceleration Station. Force of Delphi and Momentopolis are kind of beyond the scope of this unit right now. So we are going to leave those alone for the moment, for the time being. Remember for a position time graph, like this red line right here, if that was our position time graph, that would represent something that started very slow, started from rest, maybe like these red dots right here, and then got faster and faster in the positive direction. Remember, the slope of this line is our velocity. So we have to start with zero slope and we're increasing our slope. That means we're starting slow with zero velocity and increasing our velocity. Also remember that the area under a velocity time graph is position. Okay, and so when we're looking at something like this blue line right here, this blue dot, something moving constantly in the negative direction at a constant speed, we'd have a constant negative slope here, and we'd have a constant negative velocity. If we want to know how far did this thing go, or what's this change in position, we could just get the area under that graph, and that would give us our change in position. In the same way, we can go from a velocity to an acceleration. Every time we move down in this map, we're using the slope of the line to get there. So the slope of a velocity time graph is an acceleration. Okay, every time we want to go up from the acceleration to the velocity, for example, the area under the acceleration graph is our change in velocity. And so it's consistent in that way. And so to find, for example, our acceleration here, we could take our change in position, find the slope of that, change that into a velocity time graph, and look at what the acceleration versus time graph would look like, which is going to be just a constant positive line in this case. Okay, so that's a really quick rundown of what we hopefully already know about our kinematics graphs. If we change this into kind of a rotational world, we're changing things a little bit. And the way that we're changing them is just by the units that we're using. And so instead of a, or a X here for position, we have a theta for an angle. We could have the same exact graph here. The slope could start zero and then increase as time goes on, and that would represent something that maybe started at 0 degrees, and then as time goes on, kept rotating and increasing the rate that it was rotating. So it started spinning faster and faster and faster, and that's represented by an increasing slope on this line. If we had something rotating the other direction, kind of represented by these blue lines that was rotating the same rate all the time, it would be represented by this blue angular position versus time graph. Okay. In the same way that position time graphs, the slope is the velocity, the slope of an angular position time graph is our angular velocity. The area under an angular velocity time graph is a change in position in the same way that it was before. And so we go down to our angular acceleration, and it has that same relationship. The slope of an angular velocity time graph is our acceleration. The area under an acceleration time graph is our change of velocity. I think I said that wrong before. The slope of a angular velocity time graph is the acceleration. And so hopefully that helps. It's not something we have to completely learn over again because we've already learned how to do this with our position and time and velocity. We're just talking about how fast and at what rate something is spinning instead of how fast and at what rate something is moving.